Well, hello everyone. My name is Jordi Valls. I am a system administrator at EMBL-EBI. And in this presentation, I will shortly explain who EBI are, how we are using GPFS, and we'll go a bit deeper on kind of a technical problem that we have had when we have been using MMAP-based applications. So we'll explain a bit about that. I will do only the first half of the presentation. The second half will be made by Sven. He will explain what he has been working on to try to fix the problems. Who are EBI? We are a bioinformatics institute, so we are basically life science data provider. So we are part of a large network of research centers in Europe called EMBL. And our main duty is basically we receive data from many of our collaborators, laboratories, etc. It's usually raw data. And we process this data, we curate it, and we finally offer this refined data to all the life science community. So our main duty is data providing. IT services at EBI are managed by what we call the technical services cluster, which is composed by 5 teams. Every team is focused on a specific area, like web applications or web services, web development, cloud, virtualization, other applications integration, and finally systems infrastructure, where we belong. It's mainly composed of compute, storage, network, and data center, and we are part of between compute and storage part. In terms of infrastructure, we have 3 data centers with around 200 racks of equipment. We have 1 data center in Kingston, 1 in Hemel Hempstead. Those are the main ones. And then we have a data recovery site in Flint Cross. In terms of compute, we have around 40,000 cores. Sorry, most of them are building HPC-like clusters, and we also have a Hadoop cluster for data analysis. Our infrastructure is in terms of hardware is mainly blazed and mostly Ethernet-based. We had a specific cluster based on InfiniBand, but it's mostly Ethernet. In terms of storage, we have over 140 petabytes of storage capacity. We use multiple technologies and vendors in order to store our data. We have NFS-based systems like Agilent or NetApp, object store like CleverSafe, and also parallel file systems like GPFS or Lustre. The annual storage growth that we usually have is between 40 and 50%, which is quite a headache for us in terms of trying to provision for next year purchases. So across the multiple services that EBI offers to the community, one of the most popular is the EBI public tools or EBI public services. This is an integrated portal where users can run multiple tools, usually related to bioinformatics, like FASTA, BLAST, or EMBOSS. And they can run these tools directly with a web interface, accessing the EBI data with no need of knowing where the data is or having any knowledge about how to submit jobs in a cluster or anything. So every submission in this web in this web portal becomes a job that runs in a cluster, and it accesses or reads the release data related to that project. Meanwhile, all the public services infrastructure is running in one of the data centers, which is Hemel Hempstead. The data release update process is run on the other data center in Kingston, because it's where all the incoming data comes and where all this data is processed. So we basically, on the other side, on the Kingston side, we receive data from collaborators or other laboratories, and our users process this data with the cluster in Kingston, and they generate a new release. This release will be updated, so next time when the new release is ready, the tools will be updated to read the new data. So to implement or to bring this model to production, we built an infrastructure based on GPFS. So basically, we have 2 GPFS systems, 1 on each site. Every system is composed by 8 NSDs, so we have an overall capacity of 3.5 petabytes, roughly speaking. So in terms of file systems, we have built 2 file systems. One is the release one, which is the one that is replicated. So this is a sync replicated file system. This file system is composed by NSDs on each site, some on Kingston, some in Hemel Hempstead. And it's always replicated from Kingston to Hemel Hempstead. That means that our users, they generate and they write all the new data in Kingston, and it's automatically replicated on Hemel Hempstead. These file systems are mounted via native GPFS on the clusters, and also on a set of gateways or protocol nodes that will export these file systems using Ganesha via NFS to other VMs, to the cloud, to containers, etc. Apart from these release file systems, we have also what we call backup file systems, which are basically scratch areas that both sides can write, so they can any need of writing log files or temporary scratch data, they can use these file systems. But the release file system is always read-only on Hemel Hempstead, so the services can always only read, but not write. In terms of generating a new release, every time our users need to generate a new release, what basically they will do is create a new snapshot, and then from the services point of view, using Symlinks, they can choose what snapshot they want to use, so they can move from one release to the other. And the process of updating any release won't have any impact on the services because they are always using the latest snapshot. So the real problem that we have had is we are using a set of applications, and one of them is called BLAST. It's an alignment tool, and it's very popular in bioinformatics. It was developed by the EBI. And when we moved from the old system using NFS-based file system into GPFS, our users reported that the system was very slow. Sometimes the performance showed a degradation that was 80 times slower compared to the previous NFS systems, which was quite of a problem for us because we had encouraged them to move to the new platform. So, for instance, as you can see in this graph, this shows the average runtime for one single job using a different amount of technologies. As you can see, the first half shows multiple platforms based on GPFS. There is Lustre as well in the middle. So you can see that some executions take up to 86 minutes to be run. Meanwhile, NFS used to take between 1 and 2 minutes. So this is quite a problem, because especially every one of these jobs means that there is a person on the other side of the screen waiting for the result, because these are web interactive submissions. So we cannot expect the person to be waiting for 80 minutes to get the result to his job. So we tried multiple approaches to the problem. Yeah, we first followed sysadmin best practices, and we blamed the users. But in this case, they were right. They were doing the things right. And so next thing we tried to recompile BLAST using all the optimizations, install the latest version of BLAST, update the GPFS client to the latest version on the client side. We also tried to use NVMe, either using LROC or mounting a ZFS system. By the way, thanks Gurdip and D8, because thanks to them we could try this using one of their appliances. And but unfortunately, none of these solutions worked. So in the end, we tried to dig a bit more about the problem, and we found out two interesting facts. One was that this performance degradation was only happening when we were executing multiple threads in one single host. It was not happening when we were running one single host. It was not running when in any other situation. And also, using strace and analyzing what was happening when we were running BLAST, we could see thousands of MMAP calls. So that rang as a bell, because we are aware that there are some problems between using MMAP calls and using a parallel file system, and this includes, of course, GPFS. So going a bit deep on that, what we realized is that in the end, the cause of all the problem is that mmap causes the IO to fall back to the default kernel page, which is 4K, instead of using the default values that we had defined for GPFS, that in our case was 2 MB. So here we can see, for instance, this is the output of an MMDAC run. We can see the first part is a multi-thread execution. The second one is a one-thread execution. So you can see that in the first one, we are having reads of 8 sectors, and in the second one, we're reading 4,096 sectors, which is the expected 2 MB size. Going a bit also to the source code of BLAST, we can see in some of the functions that they, even in the function comments, we can see that they are expecting to use an internal mmap function when the tool is executed with more than one thread, and that won't take place when the number of threads is 1. So it was pretty clear that this was exactly the problem that we were having. So what was the next? So we tried to provide the workaround to our users. Of course, they are using Blast against NFS temporarily, but the problem was that running Blast with just one thread, although it doesn't have this penalty in performance that we have seen when running multiple threads, it still takes too much time. It's between 5 and 7 minutes, and that is too long for an interactive tool. And we tried to encourage to try an MPI solution because we are aware that that doesn't happen when you're using MPI, either if you're using one single node or multiple nodes, but that happens to be too complex to be integrated with the current software stack and infrastructure they are building. So at this point, we looked for help, and we asked on the GPFS users group list, and we made contact with Sven, who very, very gratefully offered to help. So we are aware that Sven is working on the problem, and now he's going to explain a bit of what he has been doing.
Thank you. So I know that we had problems with MMAP before, but I wasn't sure immediately if that's the same problems that we already identified or these are new problems. And it turns out it was a kind of a mixture of both. So therefore, I decided to kind of create a presentation that talks a little bit about, okay, I think it automatically moves forward. I don't want that. But so let me explain you a little bit what the problem is. There is also one future-looking slide, or actually two future-looking slides into this. So any of that can change without further notice. This is the typical, disclaimer I have to make on future-looking things. But let me tell you first what the current problem actually is, this one. So in the 4-point release of GPFS, there is a couple of very heavy locks that are exclusively protecting the MMAP pass. And so when you actually add large number of threads, it's not help at all because everybody's contending on this, what's called the internal MMAP thread. Okay, so there is basically this very heavy lock that everybody's contending. So multiple threads won't scale at all. The second problem is there is a new fast pass that we implemented about 2 years ago. And the fast pass was moving over stuff. I don't know why. Okay, I have to press fail all the time. So the fast pass was implemented a couple of years ago, and we moved over pretty much most of the other important workloads. But MMAP was never moved to this fast pass, so it still used that old slow pass in the code. Interesting. And so because of that, there's also a couple of other things that did not work well and did not scale well. There is also no sequentiality detection at all in the current MMAP code. There is no prefetching, there's nothing. And every I/O you do from the application, irregardless of what the application does, it always turns it into basically 4K I/Os or page size I/Os on Tower would be 64K. And there's also no automatic detection of parallel streams. So now it can switch over automatically, great. and so to make that a little bit more visible, I created this funny graph. So what you see basically in the upper one thread comes in and it reads sequentially 4K, 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 because that's what it looks like to us from the MMAP the application point of view. And therefore the GPFS client sends 4K, 4K, 4K reads to the NSD server. So basically there is no prefetching, there is nothing. And you basically, for every single read operation of 4K, you need to basically wait for a full round trip time over the network to the NSD server and basically reading the data back. So in the 2-thread case or multiple thread case, it's the exact same thing. So in both cases, there's basically absolutely no scaling at all. And so basically everything turns into random. There was in the code itself an optimization. If you only use one thread, then don't use MMAP. And that's why it actually did any prefetching at all. But as soon as you go beyond one, it basically degrades. So in 5.0, we added a couple of code changes into it, which already fixed this heavy locks at the very beginning. And so we no longer acquire this heavy MMAP lock on reads. So now that this lock is gone, it basically bottlenecks on other locks behind this, but at least this one single contention point where everything basically goes down to one single lock is disappearing. We also converted it to use the fast pass. So it actually is allowed to use cached objects from before. So what old pass and old pass or slow pass and fast pass basically mean, instead of every operation we check is this file is managed by DMAPI, if Windows is accessing it. So there's multiple checks we have to do all the time. And then the fast pass is actually caches all of that. So for every subsequent read or write operation, it doesn't have to do all these checks over and over again. So and that's why it's called the fast pass instead of being the slow pass. And so in this way, now that we use the fast pass, it also allows us to do detection of sequentiality, at least for a single thread on this file. And it also allows us to enable essentially the prefetching code now. Given that we can detect sequentiality, we can now also prefetch. So what this turns into in 5.0 now is, that's why I see a green smiley for the first time. So when the application now does 4K, 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 we detect, oh, there is 2 subsequent 4K requests coming in. So now the third request is going to be promoted to a full block read. That's why I see this M1M read basically behind the 4Ks. So the next read is going to be a full block that assumes a 1 megabyte block size in this particular scenario. And then it actually calculates how many blocks I need to read ahead in time to make sure the application actually never has to wait for an I/O. And so this way, you basically now get very, very nice performance because everything is already in cache, and it's just basically the thread from the application picking up data out of cache. So the latency of I/O essentially becomes 0. And that's exactly what you want. What this code does not do yet is, which you see basically on the bottom line is, if you use multiple threads in parallel, because it doesn't have that detection of multiple thread patterns yet for sequentiality, it still does move basically between sequential-ish, we call this fuzzy sequential, and full random. So it's still faster than the old code, but it's not really doing prefetching in any predictable way. And so that's basically what we're working on right now. No commitment on that, exclamation mark. So basically what we're doing right now is we implemented multiple thread sequentiality pattern detection. So that then essentially promotes individual requests to full blocks. And you see this here very nicely on this graph now. So what you basically see in the single client, nothing is changing. It's the same thing that what we deliver already in 5.0. But the bottom one is the thing that actually really changes now. What we do now is we detect that there's basically multiple streams reading in parallel in the file. And so we're going to promote all of them to full blocks. That's the first step we're going to do. And after we're going to do this, we want to enable multi-streamed prefetching within the code. So the first iteration, as I said, that we're working on, which is more near term, is going to at least do full promoted blocks. That's going to make it, that alone is going to make it like 20 times faster than it was before. And then we're going to do the prefetching on top of that. And then you basically will see massive scalability across multiple threads at the same time. And because I don't want to post backward again, thank you. That was the end of the presentation.